we investigate, report on observations in regard to their use in hazard monitoring, data assimilation, verification. The weather forecasting, which is the more sort of traditional domain of Thorpex, the predecessor to HIWeather. And so that involves atmospheric modeling, ensemble forecasting, and then the coupling to the hazard forecast and the environmental modeling side. And we'll, of course, touch on some of the downstream aspects of the integrated value chain. But the primary focus of our work is these first three the peaks here. So what this talk revolves around, or is drawn from, is a paper that we recently published in the Bulletin of the American Meteorological Society. It's in press. It's a rather large paper. It almost collapsed under its own weight. It's available on the AMS Journal's website. And it's co-authored by the entire team on multiscale forecasting, and expertly advised by Brian Golding, and there's very much of Brian's input into many of these slides. So what the paper comprises is a review of many of the aspects of multiscale hazard forecasting, including observations, nowcasting, data assimilation, ensemble forecasting, and couple hazard modeling. And so we discussed there some of the ongoing work and also some key challenges in each of those areas in research and in forecasting. Now, that being said, I'm not going to cover those here. That these areas were covered a couple of weeks ago in a HIWeather webinar that several of you may have attended. And there are several speakers from our theme and also some other experts in the field who discussed, for example, ensemble nowcasting, novel types of observations, novel data assimilation techniques at very high resolutions, hazard prediction, and fire atmosphere interactions. So this is a really interesting session, and those sort of pick on some of the key topics that were presented in the paper. So what I'll present here is 4 case studies that were used to motivate the paper from global high impact weather events, and then some of the key challenges that we identified through investigating these and some of the other case studies. Now we'll just wrap up with a few priorities. So the first case here is a case of some serious wildfires in the Australian state of Tasmania in January 2013. So this was around the peak of tourist season there, and it lasted over a couple of days or so. And so this and the following 3 slides for each for different cases sort of shows the multi-scale aspects of each of these events. So for this particular case, the seasonal forecast suggests that there are higher probabilities than average of high temperatures, largely due to warm ocean temperatures in the Indian Ocean. And also 4 years prior to this event, that there was a major wildfire event in Australia, and so there was heightened public sensitivity to the potential occurrence of wildfires. On the forecasting side, moving from seasonal scale to synoptic scale, that as with many wildfire cases, that these occurred when there was a large high pressure system that sat over the area, and that was well captured in the global models and ensembles. Then the challenges came on the short range, where there were research models that captured the local fires, and those were initiated really at the time the fires themselves were initiated. And based on those research models, that fire danger warnings and fire bans were issued. The main take home for this particular case, and this was in 2013, was the need to operationalize many of these research models and evaluate them. That they had showed a lot of promise. And I wasn't awake, but the first series of talks in today's workshop, that there are many speakers from the Bureau of Meteorology, and it'll be useful to look at some of their talks once they're available to really get an updated idea on the current status of fire danger warnings and the modeling that goes along with it. The next case was a flooding event that affected much of northern and central France. And there was considerable inundation and mudslides in many municipalities, several of which were fairly heavily populated. In this case, there was a frontal system, and in the medium range, this was caught fairly well in the ECMWF ensemble, suggesting fairly high probabilities of extreme rainfall in this general area. As with many of these flooding events, they lasted over multiple days, about 5 days or so, as the front slowly moved through and triggered more thunderstorms along the way. Many rivers burst their banks or reached record high water levels. In regard to the forecasting and warnings, the Météo France issued a very large number of heavy rain and flood warnings with different categories of alerts here. There was hydrological modeling that was used in 2016, and the general take home from this in regards to the forecasting was that the overall forecasting was fairly good, but then there were discrepancies in the exact areas where the highest flooding would occur or was forecast to occur. There was uncertainty about the uncertainty itself, and also the impacts of the flooding was not totally captured in the forecast. That being said, I'd like to point you towards Olivier Caumond's presentation from earlier today in this workshop. That he gave a great presentation that discussed some new real-time nowcasting ensemble products on flooding inundation that he and colleagues have been developing. So there's been a lot of great work over the last few years, and it's ongoing on the development of coupled meteorological, hydrological ensemble systems. And the next two cases focus on tropical cyclones. First, we have a Typhoon Hutto, which hit coastal China in August 2017. Now, with tropical cyclone forecasting, generally the inklings of tropical cyclones and their potential landfalls are provided through a deterministic and ensemble forecast from global models. And so there's emphasis more so on the track and the probability that the center of a tropical cyclone may be within a certain distance of a certain location. And so examples are here in the left-hand figure here, and then also the US National Hurricane Center provides a cone of uncertainty, which is on the next slide. Now, moving to the shorter range, there's a lot of emphasis here that many people are working on that now expands beyond the track. So there's a lot of emphasis on intensity, for example, the maximum wind speed in a hurricane. There's coupling to storm surge modeling. In this case, this was run by the National Oceanic Center of China, that these wind-driven storm surge models were around 12 to 24 hours in advance of the impact. Not shown here is rainfall prediction, and Rebecca Emerton gave a great talk earlier in this workshop, where she pointed out the importance, in her case for Mozambique cyclones, of accurate quantitative precipitation forecasting and the issuance of warnings based on precipitation. So in the short range, those models that involve more of the mesoscale and convective processes are really important to bring to operations. A big challenge in this case was the rapid intensification of the typhoon, that it reached the equivalent of a Cat 2 or Cat 3 typhoon as it made landfall, and this was not really caught 2 days in advance. And there were substantial impacts from both the extreme wind and the storm surge. This was a case of combined impacts at the same time, and the messaging of those combined impacts is sometimes quite challenging. Then another tropical cyclone case was Harvey, and so this made a hurricane in a relatively unpopulated area, or a lowly populated area of southern Texas in the United States. But most of its damage occurred a few days later, and cumulatively over nearly a week, where Harvey moved towards the northeast and weakened to a tropical storm, and sat over metropolitan Houston, where the population is about 7 million in Greater Houston. And so with the predictions of Harvey on the multiple scales, that the global models and ensembles captured Harvey's prediction very well, including a stall over northeastern Texas. Observations were used from aircraft that Rob Rogers is very involved in the Hurricane Field Program, for example. And so there is the advantage in North America of the aircraft observations, providing extra observations for simulation to better make forecasts of the hurricane track, but also the rainfall, which is important in this situation. Moving to the shorter range, there's quantitative precipitation forecasting and the probabilities thereof. And there's a range of operational deterministic and ensemble forecasts at agencies such as NOAA. And then these are provided to forecasters and the hydrologists. There's a radar network, and there are actually over 300 tornado and flash flood warnings that were issued at the time that that Harvey was over the Houston area. And so there are difficulties in the messaging there, because the response, if one's trapped in their house to a tornado, is more or less the opposite of how one would respond to their messaging of multiple simultaneous hazards. Another major challenge with Harvey was the unprecedented amount of rainfall and being able to translate that into an impact. So that was a really major difficulty. I'll just go through fairly briefly a summary of some of the challenges moving forward. I won't read these out in detail, but they're there if anyone would like to look back on them. So the first is the emphasis on preparation and the need to develop early information and estimates of the uncertainty associated with that early information to help better prepare as the event approaches. So from our group's perspective, that improving the numerical modeling and multi-scale ensemble prediction are the keys. The next challenge is enabling early action, and so that involves evacuation and also sort of where and how to evacuate, in addition to whether to evacuate. And so this is on the shorter timescales, and this involves improved numerical modeling, multiscale ensemble prediction, data assimilation, and the coupling of atmospheric modeling to the hazard modeling. The third challenge is much more local, and this is to enable a more targeted response, even at the block level in urban areas. And so this involves more sort of observations and nowcasting, examples being the tornadoes as part of tropical cyclone impacts or flash floods. And a fourth challenge is to better provide information on the nature of the threat. And so the emphasis here is on coupling the weather and the hazard models, and to better understand what that impact is going to be as opposed to just a quantitative estimate. So there are some specific priority areas for progress here. That on the observation side, these can involve advanced monitoring of the observations. That can include social media analysis, for example, but how to organizational framework for those to improve better situational awareness and reporting of these hazards. On the convector initiation side, one needs to explore novel applications of techniques such as machine learning there that may improve beyond the sort of standard NWP type process. Thinking of the smaller scales, that physically consistent initial states and ensemble forecasts need to exist on all of these scales, including the kilometer and even sub-kilometer scales. There needs to be a closer coupling of hazard prediction models with numerical models, more effective communication and use of probabilistic forecast information for the formulation of warnings and decision support products. And then on the social science side, greater research and development focus on the requirements of emergency responders and society. And just finally, sort of on the topic of case studies, spearheaded by Linus Magnusson at ECMWF, he's produced this catalog that's on this website linked here, where there's a few high-impact weather events that occur every year, and he has the various forecasting discussions, evaluations of those forecasts, and those could serve as some useful information and foci for investigating these cases through the value chain. And with that, I'll stop, and if there's time, I'd be glad to take any questions. Thank you.
Okay.